Okay, we're going to look at frequency tables now. I imagine there'll be some cutting and fast forwarding through this as it does take a bit of time. It's a bit repetitive, but there are some key principles at play here. So we're going to put this data in some kind of useful frequency table. This data happens to be somebody stood on the bridge counting cars every rush hour for a heck of a lot of days. So each of these numbers is the number of cars that passed under a bridge on that day in rush hour. So the first day they counted 415 cars. Next they counted 387 cars. Now we could just count that there's one, maybe two of each value in this list, but that wouldn't be very helpful. When it's got this scale of data and this much spread in it, and this quantity of data, it's often useful to group things together. When grouping data, you have to be clear in your head, and therefore in how you present it, whether this is discrete or continuous data. I've got a link in the description for a bit on that if you've forgotten what this means. But this data here, because we are counting things, it's not measurable, it's countable data, must be discrete data. So, this is discrete data, that's going to be important. When we group it, we've got to plan ahead for how many groups we need, what size of groups. We've got to see if we can find some hint of what the largest and smallest values are, how we're going to spread them up and split them up. So we've got something down in 290 here, that might be the smallest. 280, that might be the smallest. I can't see anything down at 260 or 270. We've got, do we reach 500 at any day? Yes, it's over 500 there. So we've got to go below 280 and over 506. If you go up in tens here, you're going to need 20 or 30 groups, which is far too many to be worth grouping together. If you go up in 200s, you're only going to have 3 groups, which is not enough. You really need to have at least 4 groups, and you don't want to go much higher than 7, maybe 9 groups at an absolute push. So I think we can probably do this in 50s, something like 250, 300, 350, 400, 450, 500, 550. That gets us 1, 2, 3, 4, 5, 6 groups, which looks reasonable to me. There'll be 6 groups in our data, which is a reasonable plot. So I've got a heading here for number of cars, and I've got a heading here for tally. I haven't put the rest of this in yet because we're going to do it together, and I don't like to draw tables before I've got to know how big they are. So the first row is 250 to 299. And the next row is 300 to 349. So there's a gap here between 299 and 300, and that's because this is discrete data. There can't be a day where 299.37 cars go under that bridge, because they are counting them, they're not measuring them. 350 to 499. Well, that's just bad counting, isn't it? 400 to 449. 450 to, that one should be 499. And 500 to 549. So now that I know how big my table is, I can then actually draw in the lines. I won't draw them all again because I don't know how wide it needs to be. These tallies could get long, but I can draw in plenty of stuff now to get this table started. So that's a height. Okay, so that's the start of the tally chart with some labels in. So when you're tallying, the whole point is to save you the bother of counting, to save you the effort of counting yourself. So I'm going to just work down each column, I think, to make it easy. So that's 415, which is in there, tally, cross it off, 387 in there, cross it off, 446 in there. And at this point, I hope to fast forward. Okay, so tally's done. We can put our column in now there. We can put our frequency, we can count them. So that's 2, 10, oh no, 17, 25, 7 and 1. So a useful check, and I can already see it's gone wrong, this is 6 by 10, 1, 2, 3, 4, 5. Yeah, so that should be 60 bits of data. If we just total these, we get 62. So I've got some extra data somewhere by miscounting. So this can happen, it's unhelpful, but I might whiz through it again in pencil and see how we're doing. Okay, so I think I've got the right values now. The correct values are 2, 9, 17, 24, 7 and 1, and that does it up to 60, so that looks more likely to be right. Until you've done this a few times, you're kind of less aware of how, when you see people who are sharing data with you, where errors can creep in. And that's quite an important thing to remember when doing real data analysis. You can apply that to maybe things going on right now and how accurate things are and how people account to that and how clever people deal with that. By keeping track of the total, you can make a simple check if you've got something close to right. So I think these red values are probably right now. And, oh no, we're not done yet. That's just discrete data. We've got the second data set here. I really hope the fast forward function's working. So, this data here has been measured, and it's measured in grams. So if you've seen the discrete continuous video, you will know that once you're measuring things, it is continuous data. And that changes slightly how you set up this chart. So the first bits are the same, the smallest and largest, what range we need to cover. We've got as low as 64 there. Yep, 64 looks pretty low. You've got 72s floating around, or 73 even, as it rounds up. We're going to get from 64 to 73, which is almost 10, so we've got in 2s, you should be alright. So something like 64, 66, I don't know what I'm doing, 66, 68, 70, 72, 74 to cover the full range. That gets us 1, 2, 3, 4, 5 categories. Now here, if we write it like this, if we do something like 64 to 65, we do 60, sorry, these are the 5 gaps if we go up in 2s. If we do it 64 to 65, anything that measures 65.3 wouldn't count because that's not in the 65 range, and it wouldn't fit in the 66, 67 range. So this won't work here. Even if I try and be something clever like 64 to 65.9, there's still a gap between 0.9 and the next 66. Even though I chuck an extra 3 9s on the end there, there's still a gap from here to that value, and there's no gap in the possible masses of clementines. Whilst there might be a gap in the accuracy written down here, the data itself is continuous. So we need to write this something with an inequality. This has got a slightly different notation you need to be aware of. So we need to have mass, which I'm going to call M, in grams of clementine. And here I want everything between 64 and 66 in the first category. Now you'll see we've got a repetition of values here. If we have a clementine of exactly mass 66, we need to be clear which box it goes in, which row it goes in, and we need to be in a way that makes sense and consistent. So the way we normally do this is we count 66 as being in this range and not in this range. So we need to be strictly less than 66 and at least 64. So we're going to have these inequality symbols in here to make that explicit. But generally speaking, everything up to and including everything up to the top bound, the upper bound, is in the lower category, and then once you actually reach 66 you tip up into the next one. So this is the 64s and 65s, point anything. This is the 66s, point anything. Tally, column, and we'll zip through this quickly. If there's an interesting value in the middle, I'll pause somewhere, maybe when we get to that one, and show you some interesting stuff. I think there aren't any point zeros, unfortunately. So here we go. Just spotted a value that's higher, so we're going to need to put an extra row in. Okay, so tallying does take time. It is a little bit tedious sometimes, but until you've actually done it a few times, you won't get an appreciation of how crucial this role is in data handling and where errors can creep in. And in fact, some of the time taken by this and the tedium of this is literally why we built computers, or why the US Census Bureau did when they first did that, to get that sorted, to make the counting things much easier. So sorry about the error, but enjoy the work.